In this video, we'll make a Rubik's Cube. We'll start with a cube. Switch to material view. Make 6 materials for the colors of the cube. Go in edit mode and assign each material to a face. Now in geometry nodes, I want to know the size of the cube. Connect the geometry to a bounding box node. Multiply the maximum by a vector having 1 on one of its axes. Duplicate the math to do the same to the minimum vector. What we are looking for will be the distance between these two vectors. If we connect that distance to the x-axis of a combined XYZ node and connect that to the offset of a mesh line, we get a line on which we can instance the same cube and it will fit perfectly. Let's repeat this for Y and Z axis. Then instance the Y-axis mesh line on the X-axis mesh line. And then instance the Z-axis mesh line on the Y-axis mesh line instances. Put all this in a group. We can put the nodes in a group by selecting the nodes and pressing Ctrl G, then name the group. Connect the count from all the mesh lines to the group input. This will be the volume of the Rubik's Cube. Let's move these lines to the center. Realize the instances, add a set position node, add a bounding box node, take the max and scale it by -0.5 and connect it to the offset of a set position node. Now if we instance the cube on these points, we see one problem. It fits perfectly and we can't see any bevel on the small cube's edges. So we are going to use a bevel modifier we made in one of the previous videos. This will give us another advantage. We can set a different material to the faces forming the bevel. We are done making the cube. We can now make the control. Add a curve object. Go into edit mode. Switch to the draw tool. We are going to draw on faces, so switch the projection method to surface. Draw several curves on the surface of the cube. Get out of edit mode and drag and drop the curve object into the geometry node we are making. Set the geometry transformations to relative. Now I want to only get the last spline geometry. So delete all other splines by taking the spline count, subtract 1 and compare all the indices. And then connect the output to the selection. We can put all this in a group. Now let's get the 3D cardinal direction vectors from this last spline. First, resample the curve to have 2 points, or I can say vertices. We will sample the position of the first point, scale the output by -1, and use a set position node to offset the geometry. Use another set position node to normalize the position of the points. This will make the distance of the line to be 1 meter. Now we need 6 points representing the 6 cardinal directions in a 3D space. So add a cube, set the size to 2 meters, then connect the geometry to a dual mesh node. We will sample the nearest point position and connect it to another set position node. We are selecting the second point by connecting an index to the selection. Put all the nodes in a group, name it to direction vectors, and now we'll sample the position of a point with an index equal to 1. This is the curve direction. Connect it to the group output. We will also need a norm of the face on which we have drawn our curve and the position of the cube vertices nearest to that curve. So let's store 2 attributes before the node group. I will name one attribute my normal and the other my position. Sample the nearest point position and store it on my position attribute. Then sample the nearest surface normal and store it on my normal attribute. Get into the direction vectors node group Sample the two attributes we created from the points equal to the index specified here and connect them to a group output. Now let's get to rotating the instances. Add a simulation zone, add a rotate instance node. Now imagine you have a vector A and a vector B. The cross product will be a vector that is perpendicular to both lines formed by A and B. So we will be rotating the cube in the cross product of A and B. A is the 3D direction represented by the curve, and B is the norm of the face on which we have drawn our curve. So add a vector math node, set it to cross product, connect the normal direction to the first socket and the curve direction to the second socket. Then multiply the output by 90 and connect it to the rotation socket.
Wait.
The rotation socket is expecting the angle value to be in radians. So add a math node, set it to radians, connect it to the vector math. Now we can connect it to the rotation socket. If we hit play and draw the curve, we see that the rotation is continuously being applied on each frame. We need to use this rotation only once, so add a switch node to it. Compare the spline count with a new attribute named move once. If the spline count is not equal to the move once attribute, we will use the true value, which is our rotation. Store the attribute after the rotate instances node. We are storing the same spline count so that the compare node will give a false value, and we will use the 0xyz rotation on the next frame. Another thing I want to add is the animation of the rotation. We will divide the rotation by 4 and we will take the spline count and connect it to the simulation output node. That means we have sent the value to the next frame. But I want to send the value to the next fourth frame, and then we store it to mark that we have used that spline. If we hit play, we will see the animation. Now let's select the necessary cubes to rotate when we draw our curve. We will take the position of the point nearest to the second curve point and multiply it by the cross product output. Then take the position of the instances we want to delete and also multiply it with the same value from the cross product vector math. And then compare it if it is equal to the vector we have first multiplied. Connect the output to the selection of the rotate instances node. Now we are able to rotate the cubes we want. How to know if the cube is solved? We can sample the rotation of one instance and then sample the rotation of each instance. Compare it if it is not equal to the rotation of that one instance. Each point will store either 0 or 1, and if we calculate the sum of all those values, it will still be 0, and that means the cube is solved. And I can use this value to switch between two meshes indicating the solved cube and the unsolved cube.